Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. So today we are going to look at one of the aspects of benzene, and basically we are going to create emphasis on monosubstituted benzene. So we had said earlier on that benzene is an aromatic compound which basically consists of a single and double bonds which are originating in this specific way. And I mentioned earlier that we can be able to illustrate benzene in two different ways or structures, which basically is the Robinson and the Kekulé structure, which are given on the board. So today we're going to look at one of the ways in which we can be able to describe the monosubstituted benzene. Basically, this one biased on its specific characteristics, especially on the effect of trying to direct some of the subsequent substituents. So for us, trying to figure out what this type of reactions will look like, we're going to have this monosubstituted benzene having a substitute over X at this specific point. So this is going to refer to N type of substituent. And of course, this basically as from a basic topic, then therefore we're going to see that this substance is going to create an impression on other subsequent substituents that are going to come in on this benzene ring. And therefore, we are going to consider the concept of electrophilic substitution reactions. And for this case, as I've mentioned, a monosubstituted benzene is the benzene that has one substituent attached to its ring. And this is going to be represented generally for us with this benzene having X given as such. So we are going to see that substituents will be directed where the incoming electrophile will attack in this specific or rather this specific benzene ring. And therefore we are going to see that the effect of an electrophile is going to be of course explained using this specific substituent. Now earlier video I mentioned that we are going to have specific names for various points in this 3, 4, 5 and 6. So we're going to have specific names for various points over this benzene ring. And if we try to give them a name, of course, let me just give them as such. We are going to have the number 1 and 5 being referred to as the ortho position. And therefore, the substituents which are going to be, of course, attached to point number 1 and 5 are going to be referred to as ortho substitution. And for number 2 and 4, we are going to have these substituents attached at this specific position. And this position are going to be referred to as the meta position. And this particular position for number 3, the substituent that is going to be attached at number 3 is going to be referred to as a para substituent. So therefore I presume that we understand this specific concept from our introduction to the benzene and similar ring systems. And therefore I'm going to just go forward with that specific aspect. So therefore I'm going to consider this specific benzene, and therefore we are going to consider this specific ortho, meta and para position insofar as the directing effect of this substituent is concerned. And in my case I'm going to consider 3 types of substituents, and I'm going to give these substituents in terms of initials. So this substituents for R is going to represent this is an alkyl groups that I'm going to give an initial R, and this basically are going to consist of a single bonds carbon that I can be able to just give in terms of that specific symbol. And then next I'm going to consider a second category of substituents, which I'm going to give using the initial X. So in this case I'm just going to perhaps create a difference between this X by giving this one as perhaps M. So therefore, let me just use this X. So X is going to be a second type of substituents that I'm going to consider insofar as directing effect is concerned. So if M consists of X substituents, which are going to include substituents with 1 or more lone pairs of electron, for instance, the nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. This is going to form a range of substituents that are going to fall under the category of X, which of course I've said are atoms with 1 or more lone pairs of electrons. And the last one that I'm going to consider in this specific case for M are substituents which I'm going to give an initial Z. And these are going to be atoms with full positive charge or largely partial positive charge. For example, you can be able to use this one. This is a metal group, and then we're going to have nitrogen in this is a nitro group, and then I can be able to consider this a specific case for a sulfur in the SO3H group. And so specifically, when I mention the nitrogen in this specific nitro group, then I refer to the this particular atom in this that is going to be in this specific group. And therefore, for this one, I'm going to consider the carbon in this, and this one I'm going to consider the sulfur in this specific molecules. And then we can be able to also to look at the carbon, of course, which is going to be contained in the carbonyl group. So the carbon in the carbonyl group is going to act as my this third category of class, which I'm going to prefer or want to consider in case if they were at this specific point, then what would be their directing effect in this benzene ring. And lastly, we can be able to look at this specific carbon in that particular group. So therefore, these are going to assist me try to figure out what are some of the positions in which the incoming substituents or electrophile will be able to attack in case if these substituents were this specific position for M. So therefore, to understand this directing effect, we're going to follow a specific rule. And of course, this rule is that the electrophile will most likely make the most stable, what we refer to as uranium ion. And in this particular case, when I talk about the concept of uranium ion, I've described in one of our videos the effect or the concept of resonancy. And resonance is the dislocation or the location of these specific charges due to the presence of an electrophile. So if it attacks itself at this specific point, then therefore we're going to see that, or perhaps if the electrons are moving within this ring system, the order in which, or the degree in which these specific ions are going to be formed, and therefore is going to assist us to determine the order of stability of the product molecule, or the product molecule that is going to be formed. Therefore, the concept of resonance is going to assist us, of course, in trying to determine which particular substituent is going to attach at that particular point, and and if that point, of course, is going to form a stable ion or not. So therefore, for the first degree substituents, for the first degree, of course, resonance structures, we're going to see that it's not going to be effective. And as we have mentioned in some of our videos, the third degree resonance structure is going to form the most stable ones, and therefore we're going to consider that one in respect with this specific uranium ion that is going to be developed. So therefore, from this is going to lay a basis for us in trying to describe the directing effect of monosubstituted benzenes in our subsequent videos, whereby we're going to consider the aspect of the meta, para, the ortho, meta, and para positions in this specific respect. So I've made this video intentionally in order to try and assist us try to have an illustrative way of perceiving or looking at benzene. And in our next video, we're going to look at the ortho, para, and meta positions and try to consider the chemical characteristics of various these specific substituents and try to see what basically assists them or try to favor them, especially on the concept of resonance structures and the uranium ion that is going to be formed as an intermediate. So that is it for now, guys. Catch us in our next video as we are going to look at the individual levels for these substituents for ortho, meta, and para positions for subsequent substituents respectively. So that is it for now. Bye. Catch us in our next video.